Two regular hexagons share a vertex and part of an edge. Let's find the length of the pink line. We're told the distance between the top vertices is 6. We need to find the length of this pink line connecting the bottom vertices. Let's call the side length of the smaller hexagon A, and the side length of the larger hexagon B. The hexagons share this vertex. Let's call it V. In the smaller hexagon, V is the upper right vertex. In the larger hexagon, V is the upper left vertex. Let's label the top vertex of the smaller hexagon T1 and the top vertex of the larger hexagon T2. Notice that T1 and V are adjacent vertices of the smaller hexagon. In any regular hexagon, adjacent vertices are exactly one side length apart, so the distance from V to T1 equals A. Similarly, T2 and V are adjacent in the larger hexagon, so the distance from V to T2 equals B. Now we have a triangle, T1, V, T2. We know two sides of this triangle, A and B. To find the third side, we need the angle at V. Every interior angle of a regular hexagon is 120 degrees. Here's the 120-degree interior angle of the smaller hexagon at V, and here's the 120-degree interior angle of the larger hexagon at V. The angle between the edges going to T1 and T2 is what we need to find. All angles around point V must sum to 360 degrees. So our angle equals 360 minus 120 minus 120. That gives us 120 degrees. To find the third side of a triangle, when we know two sides and the angle between them, we use the law of cosines. It says c squared equals a squared plus b squared minus 2ab times the cosine of the angle. Notice this looks like the Pythagorean theorem, with an extra term that adjusts for the angle. When the angle is 120 degrees, the cosine is negative 1/2. Let's apply this to our triangle with sides A and B. Substituting this value. The double negative gives us a plus. Rearranging the terms. Since the distance equals 6, we can substitute. This gives us our key equation. Now let's find the pink line. We need its endpoints. The bottom left vertex of the smaller hexagon is B1. The bottom right vertex of the larger hexagon is B2. In the smaller hexagon, B1 is the lower left vertex. Counting around the hexagon, V and B1 are 3 vertices apart. In a hexagon, vertices that are 3 apart are called opposite vertices. The distance between opposite vertices is the hexagon's diameter. The diameter equals twice the side length because it passes through the center. So the distance from V to B1 equals 2a. Similarly, in the larger hexagon, V and B2 are opposite vertices. So the distance from V to B2 equals 2b. Now we have another triangle, B1, V, B2. The sides from V are 2a and 2b. What about the angle at V in this triangle? By the symmetry of how the hexagons meet, this angle is also 120 degrees. We apply the law of cosines again. 2a squared equals 4a squared. 2b squared equals 4b squared. And 2 times 2a times 2b equals 8ab. Substituting everything. Again, cosine of 120 degrees is negative 1/2. The double negative gives us plus 4ab. Let's factor out 4. Look, we have a squared plus ab plus b squared. That's exactly 36. Substituting 36 into our equation. 4 times 36 equals 144. Taking the square root of both sides. The square root of 144 is 12. The pink line has length 12. Notice something beautiful. 12 is exactly twice 6. The distances from V doubled, from A and B to 2a and 2b. But the angle at V stayed the same. 120 degrees in both triangles. When you double all sides of a triangle but keep the angles, all distances double. This ratio of 2 to 1 holds no matter what sizes A and B are. The length of the pink line is 12. We use the law of Cosines with the 120-degree angle that comes from how hexagons meet at a shared vertex.